Thank you for inviting me. Thank you for coming to this presentation here. So I'm going to be talking about a statistics problem that occurs in infectious disease testing. There's a lot of good applied aspects to it. And also this problem involves an expected value. Expected value plays a very, very important role with this research. Now, in general, for infectious disease testing, we want our testing to be done in a timely manner, meaning we would like the testing to be done as quick as possible. We want to know, are we positive or negative for a particular disease? We also want testing to be done in an efficient manner, meaning we want a laboratory to use as few resources as possible to do their testing. During the COVID-19 pandemic, especially early on, often testing was not done in a timely or efficient manner. And you might remember cases where it would take over a week for someone to get their positive or negative test results back if they were positive for SARS-CoV-2. Now, one thing that eventually helped improve the timeliness, the efficiency of testing, was the widespread implementation of group testing by laboratories. Group testing is also known as pool testing or simply pooling in many medical applications. And back in my home state of Nebraska, I was involved in what was likely the first community-wide implementation of group testing in the entire country, perhaps even the whole world. And to describe then what group testing is and why it was beneficial, why we used it, I'm going to show you a short video of Nebraska Governor Pete Ricketts early on in the pandemic during a press conference where he's asked about what's this polling thing that you're doing? And then he's describing essentially what we were doing to make testing more timely and efficient. So let me get out of the presentation, and here's the video.
Now, the idea of this pooling means what we're going to do is we're going to get samples from everybody who we're starting to test, right? So you've heard about the nasal swab. It goes into a test tube with viral medium or saline, and that gets sent off to our lab. What we can do, and again, the idea is we're looking for the genetic material of the virus to determine if it's there. Instead of taking each one of those test tubes and testing them separately, we'll take 5 of those test tubes and put it into one and test that one test tube. And if that one sample comes back negative, we know all 5 of those were negative. And so we have just saved 4 tests. Now, if that test comes back positive, then we will have to go back and retest all 5 of those again to figure out which one of those was positive. So it's a way of really kind of narrowing down our tests. But right now, as Dr. Antone, I think you mentioned yesterday or the day before, even with all the high-risk people we're testing, right, 95% are coming back negative. So only 5% are positive. So you can see that if you're pooling these samples, you will, on balance, not have to retest them very often. You'll much more often determine all 5 are negative, and therefore you will have saved all the reagents from those 4 other tests you don't have to do because you know all 5 are negative because no genetic material for coronavirus showed up in your one test sample. Does that make sense?
Okay, so hopefully that made sense, but I'm going to review a little bit what he was talking about there. So what we did was we combined together portions of 5 specimens from 5 different individuals into a group. And we tested this group as if it were a single specimen. The reason why we did that was because if that group tested negative, then with just one test, we could say all 5 people are negative for the virus rather than taking 5 tests. And again, early on in the pandemic, it was hard to get tested or testing was done very slowly. Now, of course, if a group tests positive, then you go back to the original specimens that are in storage, take them out, and then you test those original specimens separately to determine who's positive or negative for the virus. In the end, we significantly decreased the number of tests that were needed, and that allowed us to gain timeliness, to gain efficiency. But we took those gains to now apply them to test more people. And so we were able to significantly increase the testing capacity of our laboratory. So as I said, group testing was widely used during the pandemic. One place in particular was at universities. I did look at Iowa State's web pages for COVID-19. I couldn't figure out if group testing was used here, but it was used in many different places across the world for universities terms of screening their staff, faculty, and students.
We suggested it, by the way, but it was not.
Good.
It was not a suggestion that was followed.
And I have to admit, I suggested it to my university. Our vet lab was the one who was doing all the testing and said, hey, I work in this area. I've helped people do this. Would you like my help? No. There's more to the story than that, but I'm not going to get into it right here. So government health organizations such as the FDA set up websites that say, this is how you do it. And even the news media really caught on and talked about it. So this is an article from the New York Times, the headlines of this article, where the reporters use one of our packages to help do their calculations for their story.
Any effect on sensitivity?
Oh, we could talk about that too. So that is an issue. It might be best to talk about that at the end, okay? So group testing, as you can say, is an algorithmic process, where in Nebraska, stage 1 of our algorithm, we test in groups. Stage 2, then, if needed, we go and test everyone separately. This way of doing group testing is referred to Dorfman testing. It's named after a guy by the name of Robert Dorfman, way back during World War II, who suggested this as a way to test people in the Army for syphilis. So this has a long history of being used. And while we use groups of size 5 in Nebraska, other group sizes were used around the world to do this. I think maybe even up to a group size of 100, I think I've seen. But there's also many other algorithms that allow one to implement group testing. And we'll talk about those as we go along. So then what's the role of the statistician here? Well, the role is to calculate the efficiency of a group testing algorithm before it's actually implemented. And all this is an expected value. The expected number of tests needed on a per individual basis. This measures the efficiency, how good that algorithm is going to be. The lower that number, the better. And so if I had a value of 0.25, this means 0.25 tests are needed on average to screen each individual. Or to put it another way, since if you did test everyone separately, that would be 1 test per person, you would need 25% as many tests on average when compared to testing everyone separately. That's how you interpret efficiency. And then what the statistician can do is recommend an overall best algorithm along with what group sizes to use to a laboratory. And best algorithm is the one with the smallest expected number of tests per individual. And so there's some similarities here to what the role of a statistician is when it comes to a power analysis. So a power analysis is done before the sample size is taken. You make maybe some kind of assumptions about your population or your study of interest. And, based upon that and what power level you want to have, you suggest a sample size to use. Here in group testing, the role of the statistician then is to say, okay, I'm going to make some assumptions like what's maybe the overall infection prevalence. And based upon that, recommend a group testing algorithm to use, recommend a set of group sizes to use as well. So research in group testing has been done for a very, very long time, but as you imagine during the pandemic, it really spiked up. So through my Google Scholar alerts that I received daily in my email, I ended up downloading every single paper that had COVID-19 and group testing in it, and there was over a gigabyte of papers during the first 2 years of the pandemic. These papers, as you might imagine, a lot of them were in the medical literature. So infectious disease experts were doing this, clinical pathologists were doing this. But there's also a large number of people in the non-medical areas that do research in this area, even before the pandemic, where statistics is just one of those areas. And, before the pandemic, and especially during the pandemic, reading all these papers, there was a lot of good research, but there was some research that maybe wasn't as good as it could be. Maybe by the non-medical people. Maybe they were not necessarily interacting with the people who would actually be involved with the testing. And so, at times I was thinking, okay, I think some of these algorithms that are being proposed are maybe not practical, or too complex for a regular laboratory to implement. And during the pandemic, then, there was this paper that was in Microbiology Spectrum, so it's medical literature, so the publication of the American Society of Microbiology. The authors, in their conclusion, kind of talk about what I was just talking about here. And this is what they say. While statisticians, operations researchers, and others with expertise in algorithm design have important value to add, laboratories will often identify real-world constraints that must be accounted for during the design. Statisticians and operations researchers often appear unaware of these constraints. This suggests that there are still substantial opportunities for these communities to collaborate and enhance testing capacity. First of all, I don't like the fact that they're picking on statisticians, because I think if there is a problem, it's more some of these other disciplines. And I will say I've worked with many laboratories, and I always try to think of those constraints. But this quote, in my past experience also in this area, made me want to think about, well, maybe there is some way that we could actually measure just how complex it is for a group testing algorithm to be implemented by a laboratory. And I came up with a few ideas, but I'm going to talk about just one of them here. And we're going to focus on a simple measurement, the expected number of stages to do the testing to determine who's positive or negative. And the reason why I like to focus on this measure is because each stage takes time. So for example, back in Nebraska, this was at the Nebraska Public Health Laboratory, it would take 3 to 4 hours to implement the CDC's assay to detect SARS-CoV-2. So that's one stage, one test, 3 to 4 hours. And so since each stage takes time, then I can directly convert this expected number of stages to a time measurement. So my purpose here then is to discuss the complexity for 5 different group testing algorithms. So you're going to get a nice little introduction to what group testing is, how it's implemented, and then we're going to talk about efficiency with complexity to try to figure out what algorithm might be best. And I will focus on SARS-CoV-2 testing examples, but it's important to understand that group testing is used in a wide variety of different places, even before the pandemic. One place in particular that's of interest to people here in Iowa is the State Hygienic Laboratory, based in Coralville, actually uses group testing. They use it when they are trying to detect the bacteria that lead to chlamydia and gonorrhea. And they've been using this for many, many years. I've been there a number of times and worked with them. And over a 5-year period, they saved about $3 million from doing group testing rather than testing every specimen separately. If you want to know more about what's actually done in Coralville, here's 2 of my papers that appeared in Biometrics where we do talk about that. Group testing is also used, for example, in blood donation screening. So, for example, the American Red Cross uses groups of size 16 to test for HIV, hepatitis B, hepatitis C, and West Nile virus. Many other blood banks use group testing as well. Okay, so let's get a little bit more into the math stat parts here. Let's talk about efficiency of a group testing algorithm. We're going to let T be the number of tests that are needed to screen I individuals for a pathogen to determine if they're positive or negative, where I equal 5 is what we use in Nebraska for Dorfman testing. Then the efficiency is just simply the expected value of T divided by I, expected number of tests per individual. Then in my research here, what I'm doing is proposing a new measure called the complexity. We're going to let C sub I be the number of stages for the ith individual to be declared positive or negative. And what I want to know is, well, what's the expected value of C sub I? Expected number of stages for that ith individual. This is what I'm going to call the complexity. And I don't divide by I here because essentially I'm looking at this on an individual scale. So of these 5 different algorithms that we're going to look at, we're going to start with Dorfman testing because that's the easiest to explain. And some of these expressions here are not going to be too difficult to describe, to work with. And this will set us up for other algorithms as we go along. So we're going to let G sub 1 then be the binary test outcome, 1 for a positive, 0 for a negative of that stage 1 group that's being tested. We're very interested in what's the probability that G1 is equal to 1, because this tells us that that's the probability we need to go to that second stage of testing. Then with that, then the expected number of tests is, as you might imagine, 1 for, I always do that first stage test, plus I need to do I more tests if that corresponding group tests positive. So I weight the I by probability G1 is equal to 1. That's the expected number of tests. Oops. The complexity has a very similar form. I have a 1 here because I'm doing a first stage of a testing. And then I have to do one more stage, again, if that group tests positive. So we can see that they're very, very similar, the complexity and efficiency, although they're measuring essentially different things. So what is then this probability of G1 is equal to 1? Well, derivation is actually a good exercise for first semester students, students in a math stat course. It's not difficult. I'm going to go through it here because, again, it helps us set up for some stuff that we'll do later. Again, I is our group size. G1 is our binary test outcome of that stage 1 group. Fortunately, infectious disease tests are not 100% accurate. You can have false positives. You can have false negatives. So because of that, we need to take that into account. So I'm going to define a G tilde 1 to represent the binary true status of that stage 1 group. With that, then I can start talking about stuff like sensitivity. So this S of E is going to be the sensitivity of the test, the assay that's being used, which is just a simple conditional probability. I'm going to also define a specificity of the assay as well. P is going to be my overall infection prevalence. And it's easier to do this at first. Let's assume that we have independence of among the individuals being tested. Okay, so probability G1 is equal to 1. That's what we want. What we can do is rewrite this in terms of 2 joint probabilities that allows us to get that true status in there, break up the joint probabilities into a conditional probability and a marginal probability, and then put what those conditional probabilities are in terms of the accuracy, the sensitivity, and the specificity. Probability G1 tilde is equal to 0. Probability of the group test negative is just 1 minus p raised to the I power. Again, this isn't a difficult thing. So that's Dorfman testing. Dorfman testing is often referred to as a 2-stage hierarchical testing algorithm because at most there's 2 stages. But you could have more. So we could have a 3-stage hierarchical testing algorithm. So early on in the pandemic in Germany, Lozzi et al. Described in their Lancet paper how they were doing some testing. So in their stage 1 here, what they did was they formed a group of size 30, tested that. If it tested negative, all 30 people were declared negative, just that one test. Otherwise, if it's positive, go to a second stage of testing where you break everyone up into 3 groups of size 10. Each person's represented in one and only one group. If one of these groups in stage 2 tests positive, then you go to a 3rd stage of testing for those corresponding individuals where you test them individually. So based upon what I just showed you for the Dorfman testing, well, what's the extension of complexity then to 3-stage hierarchical testing? Again, 1 for that initial stage, plus I need to go to a 2nd stage if that overall group tests positive, plus I need to go to a 3rd stage if both that group, stage 1 group tests positive, and the stage 2 group that contains that ith individual tests positive as well. So the expression is not too bad. How do you derive this particular probability? Well, now you need to define also G tilde 2, which represents the true status for that second group as well. You can go to a higher number of stages. So you could have, let's say, capital D stages in general, and we have the same kind of expression where we're just continuously adding probabilities of having to get to that next stage. Well, what are these probabilities then? Well, this is a general expression for these probabilities, and it relies on going through the same process that I showed you with that simple Dorfman testing example. Now, one thing before I got into this research, I didn't realize that I was able to basically get these probability expressions without deriving them myself, because they were all needed in the past to derive the expected number of tests. So that helped simplify what I was trying to do. And over the years, there's been a number of these people who have looked into this, with generalizations, extensions, and so on. And this is, I guess, probably one of the more general versions of this expression here. I'm not going to go through all the details of what's inside this expression, but things that we see, for example, is a sensitivity. That's a S of E. The K subscript represents which stage you're talking about. We also have an I sub A. Remember how I was the overall group size for Dorfman testing? Well, I sub A is the group size for stage A of testing, for example. Okay, so let's talk about another group testing algorithm. This is referred to as array testing, also known as matrix pooling. This was implemented by LabCorp during the pandemic. So LabCorp is, I think, a top 5 in terms of size diagnostic testing laboratory in the United States. And they submitted a request to the FDA to get an emergency use authorization to use array testing early on in the pandemic. And they received it in July of 2020. And they got the authorization for 4x4 and 5x5 arrays. Where does the array come from? Is that here's a graphic from their actual documents that they submitted to the FDA. And what we see here, what they call samples, or we can think of them as specimens, they arrange specimens in a 4x4 grid, 4x4 array. And then they form groups by row, form groups by column, and test row groups and column groups. And the reason why they do that is because let's say that second row group tests positive, the first column group tests positive, if you match them up, then that corresponds to a particular specimen that you would want to retest in a second stage. That's how array testing works. All the other individuals, which in this 4x4 grid here are represented in green, all the other individuals will be declared negative. So then building on what we saw with Dorfman testing, well, what's the complexity here? Well, again, 1 for that initial stage of testing, plus I go to a second stage of testing, if needed, with a probability of, let's call it T sub jk is equal to 1. Where this represents a binary indicator indicating that, let's say, the individual that's in the jth row, kth column needs to be retested. What is then T sub jk, though? Well, let's define script R sub j as a binary test outcome for that jth row group. Script C sub k is a binary test outcome of that kth column group. Then T sub jk looks like this. So there's 3 different ways that basically you would need to go back and retest a particular individual. The first way I've already described to you. So again, 1 means you have to go retest that person. Row J tests positive, column K tests positive. Another way is that let's say row J tests positive, but no columns. So if you sum up all those C sub Ks, sum up all the column test responses, let's say that they're all negative. So no columns test positive. That can actually happen because, again, infectious disease tests are not 100% accurate, so you could have false positives, you could have false negatives. And so now you're left with a situation of, okay, what do I do? And the safe thing is, okay, let's just go back and retest every single individual that's in that row. That's typically what's done. Also, you could have, let's say, a column test positive and all the rows test negative. Go back and test all those corresponding individuals represented in that column.
So I'm confused. So the second part has no K?
Excuse me?
No little K in the specification?
Let me do a little bit of erasing here. Are you talking about this right here? Okay. Well, it's K prime. I'm just trying to, I guess I could have just not put a prime there and put script C sub K, where you have capital K, let's say, columns. So, again, the purpose is to sum up all the test responses for the column.
How does it relate to the K in the substrate? The TJK.
Oh, well, I understand what you're saying. The key is that I'm summing up over all the columns. So let's look at that particular item that's in row J, column K, and notice how I have all the columns there. And so that's where that's coming from.
So it would be
All the column groups, we're summing up those 0 and 1 responses, test responses. We can talk about more later too. Sorry if that wasn't clear. Yes?
Why do you need a retest in the first case? Like if it's RJ is 1 and CK is 1, aren't you just done?
It could be a false positive.
That seems unlikely, but okay.
But also what can happen is this. Let's say in addition to the second row, let's say the first row, and in addition to the first column, the second column tests positive. So in that case, all 4 of these are red. You could have 4 people positive. You could have 2 people, 3 people positive. So it's often good practice to go back and do the retesting. Another reason to do the retesting is that there could be regulatory reasons, because often most often I should say, these assays are developed based upon testing separately, testing individual specimens. And you cannot formally declare somebody is positive for a disease without actually testing them separately. Okay. So then what's the probability then that I need to do a retest for that individual that's located in row J, column K? Well, these are 3 distinct sets of what can happen. And so I can just simply look at the probabilities for each of these and add them up. That's how I get the probability that I'm interested in. Again, I became fortunate when I was doing this research in that these probabilities have already been derived before. They were derived first by Kim et al. In a biometrics paper in 2007 that first described how to deal with array testing when you do have the possibility of testing error. And so she derived these expressions. And so for that, I'm not going to get into the derivation, but it uses the fundamental tools that I talked about for Dorfman testing, fundamental tools that you would essentially learn in a math stat course. So that first probability row J, column K tests positive. How do you deal with that? Well, you define, let's say, a true row response, a true column response, look at all the possible cases of what could happen, and this is the expression that you get. Dealing with then one of these cases where, let's say, all columns test negative or all rows test negative is a little bit more complicated. And I know this is a lot just to throw up, but I'm just throwing it up. And it takes a little bit of time to derive it. You can also do array testing with what's called a master pool. So to begin with, you can imagine, let's say, these specimens. Maybe they're test tubes arranged in like a 4x4 array or grid. How about you just begin with forming an overall group of these 16 individuals that are in there? That's what's called a master pool. You test that master pool. If it's negative, all 16 people are negative. If it tests positive, then you go to a second stage of testing and you implement regular old array testing. And so then the complexity for that corresponding, The complexity then for the ith individual that's located at the intersection of row J and column K is again 1 for that initial stage of testing, plus the probability that the master pool, called x of 0, tests positive, plus the probability of the master pool and that corresponding individual at row J, column K needs to be retested. That's your complexity. Again, these expressions have been derived in the past. The last algorithm that we're going to talk about is what's called Starrett testing. This was proposed actually a long time ago by Andrew Starrett as part of his math stat dissertation back in the 1950s, but over the years it's been extended, generalized, and so on. And I have a tree diagram here to explain it because this is, I think, a lot easier to explain this way. Imagine we have 4 people, numbered 1, 2, 3, 4. And we begin in stage 1, testing them in a group. If it tests negative, you're done. Everyone's negative. If it tests positive, then randomly select one person out of those 4 and retest them in a stage 2. If that's positive, perhaps you got lucky, and that is the one and only one positive. So how about in a stage 3, you regroup the remaining individuals and you retest them as a group. If it's negative, you're done. Those 3 are negative. If it's test positive, then you randomly select a person from that group, let's say it's person number 3, and test them separately in stage 4. And you just kind of repeat this process over and over again, depending upon how many people that you're trying to test. And so you can see here, by the number of rows of this tree diagram, we could have up to 7 different stages. In general, if you have I people that you're interested in testing, you have 2 times I minus 1. So how can we do the complexity here? Well, unfortunately, I didn't get as lucky with this particular algorithm because I couldn't at least directly use some expressions that have been used in the past. So I'm just going to kind of give you the big picture about how the expression comes about. So I need to modify my notation a little bit. So I have C sub I again, to mean that ith individual that we're interested in, what is their complexity? Number of stages. But I'm also going to put a superscript here, capital I, to remind me how many people am I starting off with. And then a J here to tell me who am I concerned about in terms of what order are they being tested in. So the person that's tested in the jth order. The reason why I need that is because this number 4 was tested, that person was chosen at random. This person is chosen at random and so on. So I need some way to track that. So then the expected value of this new C sub I, then is the complexity for the ith individual who is tested in the jth order. I want the complexity for the ith individual alone, overall. And so what do? You can just simply average over them. Because every individual has an equal probability of being chosen as you go along. So then it comes down to, well, what's this other expected value of interest? This is where it would take some time to go into. So I apologize, but I'm not going to go through the details, but rather give you an intuitive feel. If we go back to this diagram here, you can see this part of the tree diagram is exactly the same as this part of the tree diagram. So perhaps you could, let's say, derive some probabilities that you would need for an expected value just with respect to starting with that person number 3. Then build a recursive algorithm that builds upon that. So that if you had 4 people, 5 people, and so on, where you're always starting with this there. And that's what essentially we did. Okay, so let's now do some comparisons. I think this is perhaps the most interesting part here to see what happens with these 5 different algorithms. So I'm going to look at the efficiency of a group testing algorithm along with the complexity. We're going to use values for my infection prevalence that are low because that's when group testings typically use. P of 0.01 to 0.1 by 0.01. The group sizes that I'm going to use for these particular algorithms are chosen so that they optimize the efficiency, because that's typically how people would come into this beforehand. And so essentially this is going to allow me to look at these algorithms in a best case scenario for each algorithm. So it allows me to do maybe fair comparisons, you could say. And I'm going to limit my maximum possible group size to 15 through these group testing algorithms. And this is what I get. So I'm going to set the sensitivity and specificity to be 0.99 at each stage. On the left plot here, we have information about the efficiency on the y-axis, and then the infection prevalence on the x-axis. The black line represents Dorfman testing. So if I focus in on P of 0.01, we see that Dorfman testing has efficiency of 0.2. So essentially, it takes 0.2 tests on average to determine who's positive or negative. You've essentially saved 80% in terms of tests compared to testing everyone individually. But we can see here that that black line is always higher than all the rest. It has the worst efficiency amongst all these group testing algorithms. The other ones are better. Which ones are best? Well, notice Sterrett for some of the higher values of P tends to do better than the rest. Three-stage hierarchical testing, denoted by the red, does better for the lower values of P. But we can see also there's a lot of overlap. They're often very similar in terms of their efficiency. Then we come to this new measure, the complexity. That's what's on my y-axis now. On my x-axis, I have the infection prevalence again. And what might immediately jump out at you is these green and kind of goldish lines. Green is matrix pooling, array testing with master pool. The gold or orange or yellow there is Sterrett testing. It has the highest complexity. So it's the most complex, you could say, to implement. And so while they often have very good efficiency, these two algorithms, the complexity is not good. And this might make a laboratory think twice about, should we actually use this or not? And then let's also put this into a time context too. Remember with the Nebraska example, it took 3 to 4 hours to do the CDC's developed SARS-CoV-2 tests. So notice the expected value of C sub I here is hovering around 2. So it means 2 stages. So essentially 6 to 8 hours on average to determine who's positive or negative with one of these group testing algorithms. A normal workday is 8 hours for someone. So that means, since this is only an average, there's going to be many times where you're going to have to come back a second day and thus delay people knowing if they're positive or negative by implementing one of these two algorithms. Let's look at the black line here again. This is Dorfman testing as the second best complexity. So some laboratories, they might think, okay, I'll give up some efficiency gains so that I can have good complexity. Overall here, we see that array testing or matrix pooling, which is in blue, has the best complexity and also has pretty good efficiency as well. And I will tell you, in actual practice, Dorfman testing is used the most by laboratories for a wide variety of different infectious diseases that are being tested. And what this kind of says is that matrix array testing or matrix pooling maybe should be considered more for testing purposes. Well, what if you went to a sensitivity and specificity of 0.9? Essentially, we get similar results. Dorfman testing has the worst efficiency, second best complexity. Notice Sterrett testing, it has even gone up in terms of complexity. I did these plots on exactly the same numerical scale in terms of the y-axis and also x-axis compared to the previous plot. So if I cycle back, take a look at where that gold line is there for sensitivity and specificity of 0.99. Then when we lower the accuracy, look what happens to Sterrett testing. Complexity again goes up. Array testing still is a good algorithm to use relative to complexity, kind of middle of the road when it comes to efficiency. So let's take a look at an example. So this deals with the LabCorp one that I talked about. I'm sorry, yes?
I just have a question about the simulation study. So you said that you had a maximum sample size was 15.
Yep.
And yet for your array testing, you would talk about like the smallest like 4x4 arrays. Is there something, so that would be, if you're doing the max pooling, that you have to have 16 samples in a 4x4 array. How are you dealing with that?
Okay, so for the LabCorp case, they only use 4x4 or 5x5 arrays. The group size is 4 or 5. So the maximum group size that I allow for is 15. So you could, so for these comparisons in this plot, no, this is not a simulation study. These are.
The array with the master pool.
So yeah, now the master pool, that's the one little thing I did not mention. So the master pool would have, yes, 4 squared or 16. So yes, I do deviate a little bit from that.
But you do allow it to have, it's not like a 3x3.
I do allow it, yes.
Okay.
Yeah. So thank you for bringing that up. And one of the last things I realized before I submitted the corresponding paper for this was like, oh, I'm actually allowing for matrix with the master pool to have a little bit larger group size. So I put a sentence in the paper saying, well, in order to actually implement this, if you wanted to, well, you're going to have to allow for that. Otherwise, array testing with a master pool wouldn't really make sense. Thank you for bringing that up. Okay, so let's go back to the LabCorp example. Again, they got approval in July of 2020 for array testing, 4x4 and 5x5 arrays. And if you look through the documents that they submitted to the FDA, they give some reasoning for why they chose to use array testing, and especially at this time in the pandemic, at least from what I had seen, I only had seen one other person, one other group, one other lab, let's say, even consider array testing. And so in their documents, then again, July 2020, it was approved. They say the following about why they chose to use array testing rather than Dorfman testing. They say, Dorfman testing is not practical to implement in a high throughput testing environment where many thousands of specimens would need to be pulled and retested every day. That pulled and retested every day basically means having to go back and do some more testing in a second stage. That's what they're talking about there. Now, they didn't give any numerical evidence for why they said this or anything like this, so how about we use this complexity measure to look at that further. So we need to set some accuracy values for these calculations. In their documents submitted, they essentially say that the sensitivity for the group test is 0.977. And this was based upon thousands, if not hundreds of thousands of tests that they had already performed. And they didn't say anything about like a second stage or even the specificity for first or second stage. So let's just assume that it's equal to 1. I'll talk about what happens if it's not 1 shortly. In the documents they submitted, they provided a table of prevalences for what would happen if, let's say, the prevalence of the infection was 0.01. What would be the efficiency for array testing? So I'm going to show you that and also add to it my new complexity measure. And also, let's go ahead and put Dorfman testing's efficiency and complexity with it. And this is what we get. So we have values of P, the infection prevalence on that first column. Then we have Dorfman testing, efficiency, complexity, array testing, efficiency, complexity. I'm always using a group size of 4 throughout. And if we focus in on P of 0.05 here, we see that the efficiency is 0.43 for Dorfman testing, but for array testing it's 0.57. So Dorfman testing here has better efficiency. You'll save in terms of the expected number of tests on average. The complexity for Dorfman is 1.18. For array testing, it's 1.07. So it's less complex to implement array testing, and this matches essentially what these people who constructed the document for the FDA from LabCorp were basically saying. And so also here, you see some color-coded cells, or I guess shaded cells. The shading corresponds to which efficiency or complexity for a particular algorithm is the best. And so we see here for Dorfman testing, all the efficiencies are in gray cells, meaning that Dorfman testing always has the best efficiency. Complexity, array testing is always the best for all these corresponding prevalences. And so what we have here essentially is a trade-off between efficiency and complexity that even in other applications that one would have to consider here. That you could save in terms of tests if you did Dorfman testing, but array testing would be less complex. But I think it gets to, I like this area a lot. I think it becomes even more interesting because if you look at some of these prevalence here, the very low prevalences, look at these complexities for Dorfman and array. They're very close. So from a practical point of view, it's probably not going to matter a whole lot. But what will matter a whole lot is these efficiencies. So Dorfman testing, you'll be able to do half as many tests about than with array testing. And I would imagine some laboratories will say, hey, let's just go ahead and use Dorfman testing. So for 5x5 arrays, I equal 5. Similar results with other sensitivity and specificity levels. Now, something that you might be asking yourself was, when I was doing these comparisons here, I was always showing that array testing had better efficiency than Dorfman testing, which is different from what I saw for this previous table. Well, why does that happen? It's because we are not using optimal group sizes. And this shows you some of the constraints that might happen in the real world, that you can't necessarily use the group size that you would like to. And because of that, then I think also this leads one to say, you have to look at this on kind of a case-by-case basis to see which algorithm would be best given the constraints of the laboratory. It's also important to know here that American Red Cross, I told you about how they use group testing. Well, they use Dorfman testing in a high throughput testing environment. They test millions of blood donations per year. And while LabCorp had issues with it, American Red Cross does not. So to conclude here, so I have a few slides. So which algorithm to use depends upon laboratory priorities. Among these 5 different algorithms here, if you have optimal group sizes, it's hard to beat array testing maybe. But when you have non-optimal group sizes that you have to use, then you might want to consider looking at this much more closely. Ideally, it would be great if a laboratory would always talk to a statistician before they actually implemented a group testing algorithm. So they can work with the statistician to determine which algorithm is best to use, what group sizes to use, and so on. But I know that's often not going to happen. And so what I've done is, and my colleagues have constructed a Shiny app to help laboratories do some of these calculations themselves. Here's just a little bit of a screen capture for one of these Shiny apps, or from the Shiny app. So on the left here, we have a menu, and you can see we have hierarchical testing, we have array testing. So if I click on calculation there, that would take me to a screen that looks like this, where someone can enter in what's the overall disease prevalence, let's say the sensitivities, pool size you're going to use, click on calculate, and here we go. Here's the efficiency, here's the complexity, and this matches the P.05 case that we saw with the LabCorp example in terms of what the calculations are. And lastly here, so I showed you that quote from the microbiology spectrum paper. And they were talking about how statisticians, operations researchers, and others maybe don't necessarily know about some of the additional issues that a laboratory faces when they're actually doing this. And I would imagine that they're not necessarily only talking about, let's say, the number of stages that an algorithm needs. And what I would expect is that some of the things that they're talking about, so this is kind of a non-stat thing, is the issues with pipetting. So pipetting means, you might be, let's say, transferring. I guess I'll bring this out. I have enough time. So here's my trusty pipette. let me get my pipette tip up here. So this is what somebody in a laboratory would use to actually, let's say, transfer parts of a specimen from a test tube to, let's say, another test tube to form a group. And there's going to be more of doing this with group testing than there would be if you were to test everyone separately. And if you're doing all these by hand, that might take a while. You will maybe run into repetitive use injuries that actually came up with an issue in Nebraska that was discussed because they were forming their groups by hand. Fortunately, some laboratories do have robotic pipetting instruments, but some do not. And so if you had a robot doing this, hey, that will greatly simplify life. But even if you do have a robotic pipetting instrument, it can still take time. So in Israel, they widely use group testing to screen people. And one of the early papers that they talked about how they did it was actually using an algorithm different from what I presented here. They would start off with 384 specimens, and they would have a robot do the pipetting. It would take 5 hours to form the groups. That's obviously not a good thing. You know, if I told you it took 3 to 4 hours just to do the test. If you're a more sophisticated robotic instrument, they got that down to 1 hour. It's still some time. At the State Hygienic Laboratory, I've been there and I've timed it, and they can actually do 4 groups of size 4 at a time in 4 minutes. And that's not too bad, but they have hundreds of specimens that they need to test per day. And so you do these 4 groups, then you do these 4 groups with the same instrument, do these 4 groups with the same instrument, and so on. So it does take time. You know, might, depending upon how many specimens they have, maybe 30 to 60 minutes. So these are some other constraints that maybe some of these non-medical people are not necessarily considering when they do this research. Another non-stat issue, let's say, is laboratory information systems. So this is where these results are recorded about who's positive and negative in the end. Some laboratory information systems are not easily, let's say, amendable to including group results in them. And so I've actually been in a lab, and this wasn't the Iowa lab, but in another lab where, and it wasn't Nebraska either, where they actually put on a piece of paper if a group tested positive or negative. And worked well for them because they didn't have a whole lot of groups that they were testing per day. But if you could imagine, let's say in a COVID-19 situation where we had lots and lots of people we needed to screen, that would be a problem. So anyway, so some interesting non-statistical issues here. So that's all I have here to talk about. Thank you very much again for inviting me here. And are there any questions?
So all of your probability calculations assume independence.
Yeah.
I've actually dropped samples at the State Hygienic Lab.
Okay.
And right behind us comes a car from Grinnell. Grinnell has college. They have taken all of their samples from the past day and delivered them en masse.
Mm-hmm. Mm-hmm.
And I would imagine that there is likely an incidence in that collection of samples might be different than the incidence statewide. So you really got in reality, testing mixtures of prevalences.
Yep.
How would that change things in a practical way other than just making the computations more difficult and more assumption laden?
Sure. So there's actually 2 interesting ways to handle that situation, what you're talking about. So myself and my colleagues, we came up with a way to do group testing we call informative group testing, where we use extra information that might be available to us. Let's say some people have more risky behavior than others. And so that you can assign essentially a probability based upon their behavior, using some kind of statistical model, and then take advantage of that to do the testing in an efficient manner. So for example, I know in Idaho, at least at one point, I don't know if they still do this, they would simply separate high risk from low risk. Do the high risk individually, low risk they can do group testing on those. And so if you have information to, let's say, covariate information, if you have that information, you can incorporate that into the group testing algorithm. Otherwise, if you don't have that information, there is research out there that does deal with dependence, and that you have correlated individuals. So for example, one of my PhD students, shortly after the pandemic started, she got a job at the Air Force Academy. And so what they were doing was that they were pulling by dorm room, essentially. And so we have a correlated structure. And what they found out, or let's say rediscovered, it was actually 10 years ago in the biometrics paper where it was first discussed, that, like, and they were just doing Dorfman testing, you will have a smaller expected number of tests, smaller tests, because of that correlation. Because what's going to happen is that the people that are positive are going to appear closer together. And so if you're grouping those people together, you're going to have less groups that test positive. Thank you. That's a good question.
Any other questions?
Did you talk about a case where in the array testing, instead of one sample in a cell, you have a group? That's sort of, I guess, some sort of a hybrid of array and Dorfman. I don't think that was in your example.
Well, in terms of, let's say, creating that grid of specimens. So each specimen would be totally individual, separate ones, and then we form row groups and column groups. I do not have, let's say, one cell that's already, let's say, a grouped specimen.
Yeah, like what if your cells were groups of 4?
I mean, I did, to some respect, that kind of reminds me of, there's other versions of array testing, such as 3-dimensional array testing. And that kind of would be like that scenario. There was, by Kim et al., they did the original array testing paper in 2007, biometrics. In 2009, they did 3-dimensional arrays, 4-dimensional arrays, and so on. And basically what they found is that going to a higher dimension has only little benefits, and those benefits are for the extremely low prevalences.
So, any more questions? If no, so let's thank Dr. Bilder.
Thank you.